I have to say that Uzbekistan has for a long while been on the top spot of countries I wanted to visit because of culture and food and all that we have here. So I'm very, very grateful for the organizers of the conference, of the workshop, for putting together this workshop and for having me here. It's really, really a great pleasure. I love Samarkand, and it's just very, very beautiful. If you remember yesterday, Professor Popov told you about the tribology for everyone and how the method of dimensionality reduction can be applied to axisymmetric and non-axisymmetric, in the sense that they are almost axisymmetric contact problems of homogeneous linear materials. And I today will show you the formalism, how this can be generalized for arbitrary inhomogeneous, still linear materials, but inhomogeneous materials. So, but the problem is that it's slightly less practical than the homogeneous case. So one might say in a provocative way, this is like tribology for everything, but not for everyone. But it's very, very comparable to what Professor Popov told you yesterday. So what do I want to speak about? Well, of course, lots of materials aren't homogeneous for various tribological reasons. We put coatings to improve wear and friction properties. Nature designs materials almost exclusively in an inhomogeneous way because it's just better mechanically and tribologically. And of course, nature found that out. We found out, but nature found out a lot earlier. So in teeth or in joints, or basically any biomaterial is an inhomogeneous material. In some sense, it's either layered or it's functionally graded. So what do we do with that? And we can do contact mechanics for these materials too. It's slightly more complicated, but we can do it. I will now start with some fundamentals that Professor Popov skipped yesterday, because I have the time, because I want to say a bit less than he told you yesterday. When we look at some contact problem, it actually doesn't matter whether the material is homogeneous or immogeneous. It's just a linear expanded medium, and we indent it by some rigid body, and we will have some contact area. And the very interesting thing now is that due to reciprocity by Maxwell and Betti, we can compare two contact problems with each other. The first contact problem is this one with this, well, like convex, arbitrarily formed indenter. And the second problem is the indentation by a flat punch with that face. So we have some contact area at this instant of the indentation. There's contact area A. And now we make a flat punch with exactly this face, and we indent that flat punch. Obviously, it will have the same contact area because it's a flat punch, and if we press the flat punch, then the contact area always is known. And the pressure distribution in this second problem that we just imagined, that is P star. And the pressure distribution in the real problem that we want to solve, that is P. And due to reciprocity, we can calculate these integrals where we multiply the displacement times the pressure. And if we integrate that, we get some energy functional. And due to reciprocity by Maxwell, these integrals both must be the same. And, well, the displacements for the flat punch are constant because we indent it, and the displacement is always unity because we define it, the pressure distribution like that. So on the right side, we just have the force, and on the left side, we have some functional with the displacements in that problem and the pressure distribution P star from the indentation by the flat punch. So now there are some problems. First, we don't know P star because it's an arbitrary share of the contact area, and we don't know the pressure that corresponds to it. But what do we know? We know from Mosakovsky, long time ago, or Professor Popov yesterday credited it to Jaeger, but actually the idea is older. But Jaeger formulated it in a very elegant and, well, capturable way. The idea is the following. Actually, we can understand the indentation process by during which the contact area grows in some way. We can understand it as a series of flat punch indentations with growing flat punches. And so the incremental stiffness at this instant for this problem on the left side with this contact area A, this incremental stiffness must be the same as the stiffness of the flat punch problem with this contact area. That stiffness is only the force for unit indentation. So that is just the integral over P star, over the contact area. So this is the incremental stiffness K. But if we look at Betti's theorem, and we calculate the stiffness from there by building the derivative of the force with respect to the indentation depth, the total derivative, then we have the partial derivative and the chain rule. And the partial derivative of the force with respect to the indentation depth also is just K. And that means, if we look carefully, that the second term on the right side of equation 2, this partial derivative of A with respect to the contact area, this always must be 0. Because we have K on the left side and we have some K plus something, so this something must be 0. So, and that's the very important part. What does it mean? It means that the correct contact area in any linear contact problem will always maximize the normal force at a given indentation depth. And that is very, very useful because it's the extremal principle of contact mechanics. We have extremal principles almost anywhere in mechanics, but mostly these principles are energy principles. That's a force principle. But that is the most relevant extremal principle of contact mechanics, from which we will derive a lot of stuff. So, we have to start with the flat punch. And we will start with the most trivial problem, the cylindrical flat punch. And then we build up and up and up from here. So we have some inhomogeneous, for example, layered elastic material, and we indent it by a cylindrical flat punch. And there will be some pressure distribution. This pressure distribution must be calculated somehow, either by finite elements or boundary elements. It doesn't matter, but we have to get it from somewhere. And the aesthetics and harmony of the homogeneous problem that Professor Popov told you yesterday about arises from the fact that for the homogeneous case, we know this pressure distribution in an exact form. But generally, we don't know it. And generally, it's not even possible to calculate it analytically. But of course, it's always possible to calculate it numerically by some formalism. We have to put it that we know that. It is tabulated in some way. And even if we know it analytically, from numerical perspective, it will just be some table. And we say, we know this table, either from literature or we calculated it ourselves. And then we can also define the universal axisymmetric contact stiffness for this inhomogeneous material based on this pressure distribution. It's just the integral of the pressure distribution over the contact area. And this we have to put as known. And everything else can be derived from that. That is the point. As Professor Popov showed you yesterday, there are different ways of superposition in contact mechanics. You can superimpose fundamental solutions, just point forces. or you can superimpose flat punch solutions. And this is what we will do. We will just superimpose flat punch solutions. But this solution we have to get somewhere. But if we have it, we basically have everything. From the axisymmetric flat punch, we can calculate from the extremal force principle the solution for the contact solution in the arbitrary axisymmetric case. That is also known for quite a while. You might wonder why I'm not showing you springs when I told you in the beginning that I'm basically talking about the method of dimensionality reduction. Well, of course, one can interpret or translate these equations to the language of MDR, but I will just show you the contact solution, because the solutions are actually new, but one can always translate it to this formalism with springs and so on and so forth. But that's only, it's all the same. It's just a way of thinking. So we can derive the axisymmetric solution. It's an exact solution. It's in closed form. Everything is perfect. Everything is fine. And I want to put your attention to this integral transformation H. So this H, that is kind of the equivalent MDR profile. So yesterday, Professor Popov showed you that the equivalent profile for the homogeneous case is just an arbor transformation of the original profile. Generally, it's the transformation of the profile with the flat punch solution. And because in the homogeneous case, the flat punch pressure is the integral kernel of the arbor transform, in the homogeneous case, all profile transformations are arbor transformations. In the general case, we have to transform with the pressure as the kernel, whatever the pressure may be for the flat punch. But that can be done numerically extremely easily, because that's a one-dimensional integral. If we have the pressure tabulated, we just calculate it. And then if we have the transform profile H, then we have the full contact solution according to the equations below. So what do we do if the punch is not axisymmetric, but almost axisymmetric? Or, well, it might be quite general non-axisymmetric, actually. But let's consider the case where it's almost axisymmetric. Then we indent it, and there will be some non-symmetric contact area. And Professor Popov yesterday showed you how all the solutions will look in the homogeneous case. How will it be done in the inhomogeneous case? Well, first of all, we don't know the pressure under the arbitrary flat punch. We know it under the cylindrical flat punch because we calculated it, but we don't know it for the arbitrary case. To solve this problem, we do something, well, very similar to what you have seen yesterday. We just scale the axisymmetric flat punch pressure to the non-symmetric contact region. That is an idea that originates also from Osakowski and Fabrikant. For the inhomogeneous case, this has not been done before, but it's the same procedure. So we take the axisymmetric flat punch solution, which is this P with the head, and then we just scale it to the non-symmetric contact area with the contour A as a function of phi. And we just say it's like that. And it works very well, actually. And the second problem is, how do we execute this extremal procedure? So this variational procedure that results from the extremal force principle. Well, that actually can be done in a completely the same way as Professor Popov did it in the homogeneous case. He didn't show it yesterday because it's quite a, well, involved asymptotic procedure, but it's just mathematics. It's not nothing, there's no magic involved. One sits down, writes down the asymptotics, and in the end there's an asymptotic exact solution. And the same way this can be done also for the inhomogeneous case. And then in the end we will have an analytic closed form solution for the asymmetric inhomogeneous problem in terms of basic integral transforms using the cylindrical flat punch pressure distribution as the integral kernel. Similar to the axisymmetric case, similar to the homogeneous case, it all works out the same, only the equations are a bit more tricky in the inhomogeneous case. That's why I didn't write them down, because I don't want to bother you with boring mathematics. The thing is, we of course checked it with rigorous numerical simulations based on the boundary element method for one single elastic layer, because for a single elastic layer, on the one hand, this pressure distribution for the axisymmetric flat punch is tabulated in the literature, so we can just take it. And we have a full, complete boundary element formalism for a single elastic layer based on the Fourier transform of the fundamental solution. So we have a rigorous numerical simulation, and we can compare our approximate analytical solutions to it very easily. So first, we consider the elliptical general Hertzian contact. So we have an elliptical paraboloid in contact with one single elastic layer. And we look on the contact area. This is for an eccentricity of the paraboloid of 0.6. On the left-hand side, we have the case of an unbonded layer. So the layer on the lower surface is just freely slipping. And on the right, there is a bonded incompressible layer. In gray, we have the rigorous numerical simulation, which takes quite a while, actually. And the red lines are the analytic approximate solutions, which have been derived. And it works quite well. So now you can say, OK, that's one example. What do we take with that? So we did it for a lot of elliptical paraboloids. And the numerical simulations took like days, I guess, on quite a good computer. So what do we see here? These are contour diagrams of the difference between the eccentricity of the indenter and the eccentricity of the contact area. Because people who are well versed in contact mechanics knows that in an elliptical Hertzian contact, the contact area is not just a vertical cross-section, but the contact area is tilted slightly. And that's why the eccentricity of the contact area isn't equal to the eccentricity of the body that we press in. And what we see here is the difference between these two eccentricities as a function of the eccentricity of the indenter and the thickness of the layer. So if h, the thickness of the layer, is very large, on the left-hand side, we have the solution for a half space. And on the right, there will be the asymptotic solutions for a thin layer. And on the left-hand side, we have the approximate solution. And on the right-hand side, we have the rigorous numerical simulations. And that's already for the solution for the difference. So if you paint it in that way, it will look basically the same. But we can actually estimate the error of the approximate solution here. For example, negative values for this difference are impossible for physical reasons. And of course, in the numerical simulations, there are always positive values. So the error for difference is like approximately 10% maximum. So that's the accuracy that we are working with for the approximate solution. So it's a relative error of upon approximately 10%. Here we have force indentation curves. And, well, that is working very well. And if you remember correctly from yesterday, these force indentation curves are actually obtained by just averaging the profile to make some effective axisymmetric profile. And then you take just the exact axisymmetric solution. And this works, well, just very, very fine for various values of the layer thickness. And, well, yeah, the symbols are the BEM solutions, and the drawn through lines are the approximate solutions. Now the same thing for square pyramid. So we indented the elastic layer with a rigid pyramid with square plan form. Here we have again the contact area for an unbonded layer and the bonded incompressible layer. In red, the approximate solution. In gray, the rigorous numerical simulation. Works very fine, especially for the bonded layer. But yeah, that's no coincidence. But I won't explain why. It takes a bit of time. And here again, we have force indentation curves for the indentation of a single elastic layer by a rigid pyramid. And yeah, you see that for the global contact quantities, forces, and indentation depth, the approximate solution works just perfectly. Okay, what have we obtained? A very fast and flexible analytic approximate procedure to solve contact problems for linear materials, which is generally applicable for all layered or functionally graded materials, provided they are linear, of course. And we can determine the general non-symmetric normal contact solution based only on the known solution for the cylindrical flat punch. It can be extended to contact with friction. If this reduction procedure of the tangential contact problem to the normal contact problem is applicable, which is basically always in some sense. We have very good agreement with rigorous numerical simulations for a single elastic layer, especially for the force indentation curves. The problem is it's not quite rigorous, so numerical checks are always recommended. And the solution for the cylindrical flat punch must be known. So the aesthetics and harmony of the homogeneous case, as I said, lay in the fact that the flat punch solution in the homogeneous case is known, and now we have to get it somewhere. But actually, the aesthetics kind of remain the same. Okay. Do you have questions?